let's look at another example of equilibria in aqueous solution, that of the formation of complex ions. Now, complex in this usage means association, as in an apartment complex, not complex like something that's really difficult. In fact, the ideas that we're going to be looking at here are basically just equilibria, stuff that we've looked at before, only in a slightly different way. Now, let's first define what a complex ion is. A complex ion is an ion that has one or more molecules or ions attached to it. So, for instance, when we look at the tetrachlorocobaltate 2- anion, the chlorides are attached to the cobalt. And one thing that we haven't made clear up until this point is that when we dissolve a metal into, or metal salt into water, water gets around the metal cation, and so, for instance, when we talk about aqueous cobalt 2+, what we really mean to say is that there are waters around the cobalt, and so this is also a complex ion. So this distinction we make between complex ions versus hypothetical non-complex ions is really bogus. What we're saying is that all things that dissolve in water have one or more solvents around them, and so they're all complex ions. Now, basically all we can say is that, or what we're interested in, is the idea that if we have something that's other than the solvent in the shell, then we could call that a complex ion. So people might call this a complex ion, but everything that's dissolved in water, including this hexaquocobaltate 2+, is a complex ion. Now, the reactions of complex ions, actually one more idea. This reaction is a reaction of, so waters reacting with the cobalt 2+ is an example of a Lewis acid, Lewis base reaction. That is, water is acting as the Lewis base, and the cobalt 2+ is reacting as a Lewis acid. Lewis bases are things that donate electrons. The waters have lone pairs on the oxygen, so they donate electron density to the cobalt 2+. The cobalt 2+ wants that electron density, so it behaves like a Lewis acid. Similarly, for this complex ion over here, the chlorides have lone pairs that they can donate to the cobalt 2+, and so this is an example of a Lewis acid, Lewis base reaction. Now, we introduced the special term ligand. That refers to the molecular ion that's attached to the metal. So chloride here is acting as a ligand, water here is acting as a ligand. Let's look at a reaction between solvated cobalt 2+ in water reacting with chloride to form tetrachlorocobaltate 2-. The starting material is pink and the product is blue, and so you'll see a color change. What I have here is a beaker that has cobalt 2+ in it, and I'm going to add some hydrochloric acid, and we'll see a color change. Oh, actually, I wanted to put this into a bigger beaker because I'm going to need the additional volume. And that's not too good. So we'll add some more acid. This is still hydrochloric acid. And you can see that it's forming blue streams. There we go. Okay, so that's now a nice blue color. And again, that's the color of the tetrachlorocobaltate 2-. Now, we can define an equilibrium constant for the formation of a complex ion. Cobalt 2+ reacts with ammonia to form this tetrammonium cuprate 2+ cation, and the equilibrium constant for this reaction is just the concentration of the product divided by the concentration of the cobalt, and then the concentration of the ammonia raised to the 4th power. Remember, this 4 comes from the fact that stoichiometric coefficient is 4 in front of the ammonia. And typically, formation constants for complex ions of this sort are very large. In other words, this reaction essentially goes to completion. If we take cobalt 2+, dissolve it in water, it forms a complex ion that has waters around it. But if we give it some ammonia, it prefers the ammonia, it gloms onto the ammonias to form a tetraammonium cuprate 2+, with an equilibrium constant 4.8 times 10 to the 12th. Or something that's very large. And we can also define a second sort of special equilibrium constant called the dissociation constant, K sub D. Before, the formation constant was K sub F. I may have forgotten to mention that. K sub D is just the reverse reaction. So take the cobalt, the tetramine copper 2+, and it dissociates to form copper 2+ in aqueous solution plus 4 ammonias. Being the reverse reaction, we write the equilibrium expression as 1 over what it was before, and so clearly K sub D, the dissociation constant, is just 1 over the formation constant, and some books will list formation constants, some books will relate dissociation constants, but you can see that they're intimately related to each other, and so you don't need to know you don't need to know both, you only need to know one. So how do we use things like dissociation constants? And let's go ahead and use our 4.8 times 10 to the 12th for the formation of the tetraammonium copper 2+ cation. Suppose we start with 800 milliliters of a 0.8 molar ammonia in a beaker, and then we start adding copper sulfate. Suppose we add 1/10 of a mole of copper sulfate to this solution. What's going to happen is that the copper is going to react with the ammonia to form the complex ion, and there's not going to be a whole lot of copper 2+ left in solution sort of floating around free. Most of it is going to be bound up by the ammonia to form the complex ion. Why is that? It's because the equilibrium constant for this reaction is so large, because the formation constant is so gigantic. But we can still calculate what the concentrations at equilibrium are for this species and this species. And doing that, we can, knowing the formation constant, calculate what the equilibrium concentration is of copper 2+ that's free in solution. Now, to do that, what we have to do is, first of all, a limiting reagent problem. In other words, we put in 1/10 of a mole of copper sulfate. Do we have enough ammonia here in order to make all of the copper form the complex ion? And the way to do that is we have to calculate the number of moles of ammonia that we're going to utilize. And the number of moles is 1/10 of a mole of copper 2+, that's what we put into the pot originally, times 4 moles of ammonia divided by 1 mole of copper 2+. These are just the stoichiometric coefficients for the balanced reaction. And it means that we would need 0.40 moles of ammonia to react with all the copper 2+ that we've added. Well, we have 0.64 moles of ammonia. How do we know that? Well, remember, we know the concentration of the ammonia, and we know the volume of the ammonia. We started with 0.800 liters, and we know that it's 0.80 molar. And to get the number of moles of ammonia this represents, we multiply the concentration times the volume. So 0.80 times 0.800 is 0.64. So this is the number of moles of ammonia we started with. We're going to use up 0.40 moles of ammonia. That's going to leave us 0.24 moles of ammonia left over. So we have enough ammonia for this reaction. We're going to use up all the copper to form the complex ion. So an expression of that, the symbolic expression, is that the concentration of the complex ion in solution at equilibrium is just given by the original concentration of copper that we started with, right? Essentially, all the copper is going to be converted into the complex ion. Now, that's an assumption. What we have to do is we have to check afterwards to see whether or not, in fact, almost all the copper is converted to this. Remember, when we make assumptions, if the concentration of free copper is less than about 1% of this, then it makes sense, then our assumption makes sense. So we'll calculate the concentration of the tetraammonium copper 2+ cation, and that's 0.10 moles, because that's the number of moles that we started with, divided by the final volume, and that gives us 0.13 molar concentration of the complex ion. The concentration of ammonia at equilibrium, so that's an equilibrium concentration, and similarly with the concentration of the ammonia at equilibrium is given by the ammonia that's left over divided by the volume of the solution, and that's 0.30 molar. And now we can take these two pieces of information and plug them into our expression for the formation constant. We're going to rearrange this expression for the formation constant, put the copper 2+, that's what we're interested in, by